Two on, okay. Aliba Nisar. Matthew Portugal,
Here, Matthew's fine.
okay. Daniel Cruzada,
Here.
Adrian Salas. Sophia Siddiqui,
Here.
Desiree Solis,
Here.
Joshua Torres,
Here.
Benjamin Zubi.
Here.
Okay, now I sent out a meeting link to the people who are on the wait list. So Brandon Bernard, are you here?
Yeah,
Okay, do you need a ad code?
I do.
Excuse me, Professor.
Yes.
Yeah, I came in late. I don't know if you call my name.
Hold on a sec. Brandon, try 107585. You must be Aurelio Cervantes, right?
Yes, that's correct.
Okay. Now,
Professor, I joined in
Jonathan.
late too.
I'm sorry. Oh, Danny.
I joined it, yeah.
Okay. What about Aliba? Still not with us? Okay. So Jonathan Biomeyer.
Yeah.
So you need an ad code?
Yes, sir.
Okay, try 108960.
It was approved. Thank you.
And Truck, I think I already gave you your ad code. Is that right?
Yes, you gave me.
What do you like to be called? Truck.
Yeah, that's fine. Chook is
Okay,
fine.
so I said it right?
Yes.
Okay. All right. Anybody here his name I didn't call or get you down, or anybody else need an ad code or anything? Okay, good. Well, let's start by saying that everything, I think, and you can tell me if it's not, but everything I think is on Canvas. So let's bring up the Canvas schedule and just look at it. So everything is going to be, most everything is going to be under files. You've got assignments under assignments, and of course the tech Zoom, but everything else is under files. So you have the syllabus. I expect you to read it, but let's just go to the schedule and talk about it. Okay, so first thing, we're meeting Mondays and Wednesdays, but you already know that because you're here. You can see the lesson plan for the day, what chapter we're going to be doing. I expect you to read the chapters ahead of time. Obviously, you couldn't today, but in future, I expect you to read the chapters ahead of time. The single biggest determinant of student success I have found is reading ahead of class and being prepared with questions. And that means working the problems ahead of time. Don't wait till the day before they're due and start working the problems. Work them ahead of time and ask questions in class. I expect you to ask questions about any and everything in the class. My ideal would be you read the book and I answer questions, and that's what we do. But probably you want a little bit of lecture as well. So we'll give you that. There's some comments here, mostly the quizzes. We're going to have 6 quizzes, and they're going to basically take the place of the midterm. So you're going to have 6 quizzes that'll be maybe an hour during the Zoom session. I think there might be a quiz on the day we do a lab, but that's okay. Nope, doesn't appear to be. Okay, so quizzes will be done during the Zoom sessions. They'll be about an hour. All added together, they're the equivalent of a midterm. The final will be cumulative. So everything in the class will be on the final. There's a lot of stuff to cover here. There are some exercises which you will find in Canvas under Files, Handouts. And the first one, Measurement and Uncertainty, is going to be a little different. But all the others, the way I am going to assign a grade for this is you're not going to turn them in. On the day that we go over them, I'll call on you, and everyone in the class will have an opportunity to recite at least once. And I will tell you, so what's your solution for number 4 for the free body diagrams? And I'll give you control of the screen, and you give the class your solution, just like going to the board in the classroom. If you are unprepared or not present, you'll get a 0. And you may only have 1 chance to recite in the semester. Probably you'll have 2, looking at it. But you don't want to get a 0 for that, for one of them. So you have to solve all of the exercises. Everybody has to do all of them, and you will be called on at random to recite. So you'd better be ready. Now, you don't have to have it correct. You have to be prepared and have tried. Okay? So I'll give you credit if you make a mistake, but you prepared and you tried. We talk about it. Now you understand it. Fine. That's great. But if it's, I haven't looked at this before, then that's a 0. Not going to be acceptable. That means that you need to look at these things ahead of time. And again, today's exercise is going to have to be different. You're going to have to look at these things ahead of time and ask questions in class. Say, Dr. Woodman, I looked at the free body diagrams. I don't understand number 6. We'll talk about it. Okay? Now, moving on to labs. We're going to have 9 labs. The lab manual is on Canvas, and the titles of the labs are the titles given here. However, they're not in the order that they're presented in the lab manual. So you have to go to the right one. Read it ahead of time. There will be pre-lab questions you have to answer. I expect you to answer them in your lab notebook. I will not grade them, but I'll look at your lab notebook so I'll know whether or not you're preparing and whether or not you're trying. A week after we do the lab, you'll have to do a formal lab report. And there is a sample lab report in the lab manual on the back. So you can read that over and follow it. And again, what's the rule? Issues, concerns, ask during class. It benefits the whole class when you ask a question. All of your fellow students are sitting there saying, God, I wish Jonathan would ask a question, because I got so many questions and I'm shy. So don't be shy. Go ahead and ask. Also, all of our labs will be on Wednesdays. I almost said Thursday. All of them will be on Wednesdays, and they will be on campus in room 415, which is listed on the in the schedule, in the catalog. So room 415 is our classroom for this class. We will be on campus only for the lab sessions. So on Wednesdays when we don't have a lab, we will be on Zoom. But on Wednesdays when we do have a lab, we're going to be in class. Now, sometimes we'll have some lecture in the classroom as well as the labs, because the labs really should only take about half the period, but we'll address all those things when we come to it and do whatever we need to do. Okay, so you're going to need a lab book. Going to need to read the labs ahead of time, answer the pre-lab questions. The pre-lab questions basically are always along the lines of, how are you going to analyze your data? So you need to do those before you do the lab, because otherwise you won't know how to analyze your data. Now, there's two kinds of homework: Mastering Physics and PIP, Problems in Introductory Physics. Mastering Physics is, the course is set up, but I haven't populated it with the questions yet. However, you have, in the same folder as the syllabus, you have an Excel spreadsheet with the homework problems. And there's two worksheets in that spreadsheet. One of them is the Mastering Physics problems, which are the numbers in the problems in the book, which is the 15th edition. And the others are the problems in PIP. PIP is open source textbook that I put on Canvas for you. So you go in there, pull it up, do the problems that are assigned. The PIP problems are going to be submitted by their due date via Canvas. So there will be an assignment that says PIP Chapter 1, and you will upload by the due date the assignment, and I'll grade it. Now, if we were in class, I'd have you exchange papers and grade each other's, but I guess I'll have to do it. Darn. Mastering Physics is all online. Your grade there, I'm not even going to look at it until it's time to assign you your grade, and I'll just pull off your points and put it in the grade spreadsheet. The problems in Mastering Physics are the identical number problem in the book. So in Chapter 1, I assigned number, let's see, in Chapter 1, one of the problems you were assigned was number 43. So in the book, Chapter 1, problem 43 is identical, or nearly identical, to the Mastering Physics problem. The numbers might be different, so you might have to work out different numerical answers, but the problem is the same. So you can work on them ahead of time by getting the problem list and getting them out of the book and having the answers prepared, and just type in the answers into Mastering Physics if you want. Or you can go into Mastering Physics and the problems will be there. The only problems that you're going to solve are going to be in the Mastering Physics. So only the ones I've assigned are uploaded into the system. Okay. There's instructions for signing on to Mastering Physics. If you bought the textbook separately, or if you have an ebook, or if you have the 14th edition, which is fine, you'll have to buy Mastering Physics separately instead of but you gotta have it somehow. There are instructions on how to log on, register class, all that in Canvas. I think it's called MP instructions. The folder there, MP instructions. Okay. By the way, I don't know what edition, but the content is the same, but the problems are. So if you have a 14th edition, then you're gonna have to draw problems off Mastering Physics. Okay. Who's got an issue with that? Who doesn't have that textbook? Anybody?
Yeah, I don't have it yet.
Okay. Just so that you can start reading, I'm going to put the 14th edition of the book on Canvas. I'll put under files under textbooks. I'll do that during the break this afternoon, as soon as I can get to it. So you can download the 14th edition and read that. And the reading is the same as the 15th, even though the problems are different. Maybe the examples are different, but so that you can start reading. Okay, I'll do that. Okay, anybody have any questions on the schedule or anything?
I have one. So when I mentioned reading chapters at a time, I see some chapters over normal days. would you recommend we read the entire chapter or we split up the readings?
Well, everybody is different in how they approach things. Roughly, the chapters will be split in half, but not necessarily. So on Wednesday, I'll fall in Monday chapter 2, and presumably we'll do about half of chapter 2 on Monday, and on Wednesday about half of chapter 2 on Wednesday. On Monday, gosh. Okay, you know what I mean. But not necessarily. So you should probably read the whole thing. But I don't know how you do things, and everyone has their own style. Some people just read through it, just general comprehension, and just sort of see the lay of the land, maybe. But if you do that, then go right through it. But then go back and look at each section individually and very carefully. And the way I did it, I wasn't very into it, is I would do two things. First, I would make notes out of the book as if I had to give a lecture. So I would make certain that I understood the section and made notes like you can use those at a lectern or a blackboard lecturing. And make sure I had that level of understanding. Then I would do a problem for that section. So you can figure out which of the assigned problems are in which sections because they're listed in the book that way. Does that help?
Yeah, it does. Thank you.
Okay. All right. Any other questions on the schedule?
Yeah, I have a question.
Go ahead.
So as far as the Master in Physics, you said you were going to upload it to the files. Does that mean we don't have to purchase the book anymore?
Yes, you should purchase the book. I'm going to put the textbook. The questions are on Mastering Physics, and you don't need the book to do the questions because the questions are online. They just happen to be the same as the book. So I'm telling you so you can just look at the book, if you want to solve them. I put the 14th edition on Canvas, or will do for you, so that you have something to read until you get your copy of the book. But you should buy the book. I know they're expensive. Everything's expensive. But this is your education. Is there anything more important? Is beer more important than your textbook? Well, obviously, but I'm not supposed to say that. Okay, anything else? Okay, good. So I think we've covered just about everything, haven't we? Is there anything we haven't covered? Anybody have any questions on anything? What more can I possibly say until we have to start talking about physics?
I guess I have one quick question.
Go ahead.
Like obviously you want us to read ahead like certain chapters and everything like that.
Yes.
Is there any chapter in particular that you're like, hey, really focus on this one like ahead of time? Like, is there any really dense chapters?
Yeah, 1 through 14.
Awesome.
Yeah,
Thanks.
all of them is the answer. I understand your question, but all of them is the answer. I know it would make your life easier if you were told, really chapter 12 is the most important one. You just pile on that. But that's not the right procedure. Sorry. So I'll tell you, chapter 1's kind of a throwaway. I mean, chapter 1 is always just, baby stuff. And then the hardcore stuff starts in chapter 2. But you got to do them all anyway. Let's see. Oh, I wanted to talk about scientific calculators. Okay, you have to have one for this class. I mean, I don't know how you're going to live without it. I recommend you buy one that has 2 features that not all of them have. Buy one that can do complex arithmetic. You won't need it for this semester, but you will for the second semester. And buy one that can do matrix equations or matrix manipulations. Again, you won't need it for this semester, but you will need it for the rest of your life, assuming you're going to be a scientist or engineer. So my TI-83 does complex numbers and it does matrices. And I bought this, I don't know when I bought this. I bought this a long, long time ago. I'm surprised it still works. And when I was working in aerospace at Northrop Grumman, you know, it was in my pocket every single day. I used it every single day. There was always something I needed to do with it. So buy yourself a good one. The TI 83, 84, 86, those are good ones that do the matrix and complex numbers. Casio makes some that does matrices and complex numbers. So you pick the one that you like. There is one calculator out there, and I don't remember which one it is, that will actually do complex matrices, which my 83 does not. That will be useful to you when you study AC circuits, but that won't be till next semester. But again, the best calculator ever in the history of the world only costs $100. So you might as well get one that's really, really good. Okay, so we've talked about homework. We've talked about the lab. Oh, office hours and such. Okay, so I'm not going to have any office hours, obviously, because I'm at home. So if you need anything, you have a couple of options. One is you can talk to me on those days that we're on campus, but that's only 9 days out of the semester. The other is you can ask questions during class. And the other is you can send me an email. My reputation has probably gone ahead of me. I'm notoriously bad on keeping up with email. My wife nags me about it every single day, and if it weren't for her, I probably would never read it. But I will make an effort. I promise I will read my emails. If it's urgent, just call me. If my phone number is on the syllabus, 909-306-8991. It's on the syllabus. Just call me. Anytime, 24/7. If I don't want to answer it, I won't answer it. If I do answer it, then I'll be available to help you. Leave a message. And in your message, tell me who you are and what class you're in. And what your question or problem is, or just tell me to call you back, I guess. But please let me know who you are and what class you're in. That would help. Same thing on emails. Tell me what class you're in if you send me an email. All right, do not text me. Please don't text me. Let me show you my phone. I have the dumbest phone in the history of the world. I'm the only person in America with a flip phone. Okay? This is the dumbest phone that ever lived. I can't even read text on it. So I'll get something that tells me you sent me a text and I won't even be able to read it. So don't send me texts. You may wonder, why don't I get a smarter phone? If I could get a dumber one, I would, because I hate phones. But I will answer it or listen to voicemail, but don't text. Okay, so we were going to have an embedded tutor for this class. I don't know if we will. The fellow who was going to be the tutor was unable to for scheduling reasons. I'm trying to find someone else to do it. If we do have an embedded tutor, that would be great. If not, you'll just have to ask questions during class and call me and email me. Okay, anybody got any questions on anything? Okay, good. Then maybe we should actually start talking about physics. All right. So chapter 1 is all about vectors and physical quantities and stuff like that. So let's talk about that a little bit. You probably all had chemistry or physics in high school or something, so you kind of know this stuff. but we are going to be using almost exclusively something called the MKS system, or the international system. M stands for meter, K stands for kilogram, and S stands for second. Okay, so basically we're metric, but in particular, meters, kilograms, and seconds. And all of your work should be done in this system unless otherwise required or mentioned. Okay, this is the standard. So where do these things come from? Well, all physical quantities, except for electricity and magnetism, which requires us to add one more unit, but everything that we're doing in mechanics has units that are combinations of meters, kilograms, and seconds, are dimensions of length, mass, and time. Everything is some combination of those three things. So where does the meter come from? Well, the meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. So they had to come up with some way of defining it. So that's what they did. Now that is an example of using an artifact to define your dimension. The artifact being the Earth. The Earth is a particularly bad artifact because that distance is not constant, right? The Earth is not a perfect sphere. It's an oblate spheroid mostly, but it also has some other little issues with it. For instance, mountain ranges and things like that. So 1/10,000,000th of the distance from the equator to the pole is kind of a not that wonderfully useful. So it's only approximate. So what was decided eventually was to create another artifact, which is called the standard meter. It's a platinum iridium bar whose actually the scratch marks between 2 points, the distance between two scratch marks on the bar was defined as the meter. Platinum iridium bar was chosen because it wasn't going to rust and it wasn't going to expand very much with temperature and things like that. But it's still actually rather cumbersome. So the new definition of the meter is defined in terms of the speed of light. So if you have a definition of the second and you know what the speed of light is, then you know what the meter is because you know the speed of light in meters per second. And the definition is that C is exactly, I'll tell you the number just so you can see how precise it is. That number is exact. Why is it exact? Because it is defined to be exact based on the definition of the second. And since it is exact, it tells you what a meter is. A meter is this number of them is traveled by light in a second. So that defines the meter. Okay. What about the time? Let's go to time next. The second was originally defined in terms of the rotation of the Earth, 24 hours from sunrise to sunset, which is not the rotational period of the Earth because the Earth is moving along an orbit around the sun. So sunrise to sunset is not exactly one rotation, but that's okay. Sunrise to sunset, defined as 24 hours. Each hour has 60 minutes. Each minute has 60 seconds. That defines the second. And that's good enough for many purposes. But again, it's not exact. It's not extremely precise. So the modern definition of the second is that it is based on the frequency of light emitted during a certain atomic transition in a cesium atom. So frequency is oscillations per second. So if you know how many oscillations there are, if you count the oscillations in this this light that's emitted by the cesium atom, now you know what a second is. So it's defined as that. And it's defined in such a way as to bring it into conformity as much as possible with the traditional definition of the second. For any kind of purpose we're going to do in physics class, there's no difference. Doesn't make any difference, but that is how it's defined precisely. Now, mass is more problematic. Things may have changed because I haven't kept up with the literature in the last year or two, but as of my last information, the kilogram, the unit of mass, is still defined in terms of an artifact. It's another platinum iridium bar kept in a safe somewhere in Paris. And whatever the mass of that thing is what the mass of a kilogram is what a kilogram is. And secondary standards are created from that. Those secondary standards are sent all over the world to laboratories, like, for instance, the Bureau of Standards in Boulder, and tertiary standards and farther down standards are created from that until eventually you get to a kilogram. Well, I don't even know what to call it, a kilogram weight that's in your lab bench that you'll see when we go to do labs. Okay, this is not satisfactory. It is desired to define the kilogram in terms of something else, but I'm not sure that it has been agreed upon yet what that should be. Okay, so that's the MKS system. Now, I said everything, all the units in physics, in mechanics, can be created from meters, kilograms, and seconds. For example, let's look at velocity. Andreas, can you tell me what the units of velocity would be?
Like miles per hour or something.
Miles per hour would be some disgusting British system. What would be the MKS equivalent of miles per hour? Length
Meters
over
per
time.
second. Meters per second.
Meters per second. Okay. What about density? Density is the amount of stuff in a volume. What do you think, Aurelio? What are the units of density going to be? The amount of stuff per unit volume.
Grams per liter.
Okay, well, that would be an acceptable units for density, but they're not MKS. So you must be thinking of chemistry.
Yeah, I think so. So then it would
Okay,
be,
well, in MKS, what would be the equivalent of a gram? What's the unit of mass?
kilogram.
Kilogram. And what is the equivalent of volume? Instead of liter, volume would be?
Milliliter.
No. A milliliter is a cubic centimeter.
Oh,
So volume in MKS would be?
kilogram per cubic centimeter.
Per cubic meter.
Cubic meter. Okay.
Right, right. So kilogram per cubic centimeter is certainly a density, but it's not MKS. So kilogram per meter cubed. Okay. Now volume is obviously meter cubed. I probably should have said that one first. Frequency, F. What would be, Jonathan, what would be the MKS units for frequency? Frequency is the number of times something happens per unit time.
Sorry, I was eating. Number of things, something per second.
Call them oscillations if you want.
So it'd be repetitions per second, right?
Repetitions per second or oscillations per second, whatever you want to call it. Usually we just say 1 over seconds or seconds to the -1. If you want to make your meaning perfectly clear, you could say something like revolutions per second or oscillations per second. But oscillation isn't a unit, right? It's just a word that makes it clear. The unit is actually per seconds for frequency. Now, there are related quantities to the MKS system that are called rational units. They're rational in the sense that they're powers of 10, different from MKS. So a gram is 1,000th of a kilogram. A kilometer is 1,000 meters. A cubic centimeter is 1/1,000,000th of a cubic meter. So these are, that's easy to do unit conversions. They're rational units. They're based on powers of 10 of MKS. Sometimes it's convenient to use them. For instance, when discussing density, it is sometimes convenient to say grams per milliliter or grams per cubic centimeter, and milliliters being a cubic centimeter, just because the numbers are more convenient. As long as you know what you're talking about, that's fine. In general, you should be using MKS. Unless there's a special reason, you should be using MKS. Sometimes your mastering physics will ask you to give the answer in a certain unit. That's fine. There are other units that are used pretty much only in the United States now, called the British Engineering System or its related units. And that system, the British were smart enough to get rid of it. I guess they gave it to us. Maybe it was a joke. But they're based on animal parts, right? What's a foot? It's the length of King John's foot. I mean, well, King John's dead, so what's a foot? I don't know. And things like that. And inches are 12 to the foot instead of 10. And things like that. And everyone still uses that in terms of time because there's 24 hours in the day and 60 seconds in a minute and 60 minutes in an hour. So not rational there, but that's okay. We will stay away from British system, miles per hour, things like that. We're going to stay away from that for the most part. All right. Yes.
I've actually just always been curious. Why is there so many things off of 12ths? Like a foot, a second.
Yeah, that's a good question. So I'm channeling the spirit of Sister Joseph Ann here back in grammar school. And what we learned was that the Sumerians and Babylonians didn't count by tens like we do. They counted by 12s. 5 times 12 is 60. That's where the 60 comes from. 2 times 12 is 24. That's where the 24 comes from. So it's something left over from the ancient Sumerians and Babylonians that we do things sometimes by 12s.
Thank you.
As far as I know. You could Google it. Okay. You probably are familiar from high school and from chemistry with how to do unit conversions. So let's just do an example. Let's convert 10 grams per cubic centimeter. Let's convert that into kilograms per meter. And the idea behind here is that if you multiply something by the number 1, it doesn't change. So how many grams are there in a kilogram? There are 1,000 grams in a kilogram. Well, 1 kilogram divided by 1,000 grams is just really the number 1, isn't it? But the way I've arranged these, the grams cancel, and I'm left with kilograms. Now, the centimeter is a little trickier. There are 100 centimeters in a meter. So there are 100 centimeters cubed in a cubic meter. So 100 cubed centimeters cubed. In other words, a million. Okay, but now look, the centimeters cubed cancels out, and I'm left with kilograms per meter cubed. So everybody sees how that works, right? I'm sure you did this in high school. So here's something for fun. Take the speed of light, which is this number in meters per second, and convert it to furlongs per fortnight. Thinking of the stupidest British units I can possibly come up with. Who knows what a furlong is? It's a horse racing term. I believe it's 1/8 of a mile. And a fortnight is 14 days by definition. So you have, let's do it as a more simple number. Let's do it as 3 times 10 to the 8 meters per second. Now we want to convert that to furlongs per fortnight. So let's do the seconds first. So there are 60 seconds in a minute. Seconds cancel. There are 60 minutes in an hour. There are 24 hours in a day. And there are 14 days to a fortnight. Okay, so now I've converted the 1 over seconds to 1 over fortnights. Meters to furlongs, you got to convert somehow to feet, and then 5,280 feet in a mile, and 1/8 of a mile is a furlong. So I think this is good enough, right? Everyone gets the idea? Anybody have any questions on this? Okay, good. Okay, let's talk a little bit about numerical literacy. You have a handout on numerical literacy. I will go over the high points for you. The first thing is that you should use scientific notation. And what do I mean by scientific notation? I mean a mantissa that's one figure, the appropriate number of decimal points times a power of 10. So, for example, 1,000,000 is equal to 1 times 10 to the 6. Now, I could have put 1.0, but I wrote this number as if it were an exact number, so I don't have a decimal place. That's considered to be infinite precision. I said 1,000,000 exactly. Okay. You may have a setting on your calculator for engineering notation as opposed to scientific notation. Engineering notation is the same thing, except the powers are always multiples of 3. So in engineering notation, you write numbers as times 10 to the 3, or 10 to the 6, or 10 to the 9, or 10 to the 12, or 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. So you don't always have a mantissa that's one digit. But in scientific notation, we do. I actually don't care which one you use. If you're consistent, engineering notation is fine. If that's for some reason what you're used to. But you see how closely related they are. Now, what about precision and accuracy of numbers? Let me ask you a question. So, Sophia, is that an accurate number for pi?
No.
Why do you think it's not accurate?
I'm not sure actually.
Actually, I think you're thinking of the concept of precision, not accuracy.
Maybe. Yeah.
Accuracy means correct to the level of precision that you are claiming. I'm only claiming two significant figures here, the mantissa and 1 decimal place. I'm only claiming two significant figures of precision, but that number is correct to two significant figures. What if I were to write that instead? Now, Sophia, would that be an accurate representation for pi?
Yes.
Yes, it is also much more precise than the other number because I'm claiming a greater number of decimal places of precision, but it is correct to the level of precision that I claim. Okay, so there's a difference between accuracy and precision. Now, Michelle,
Yes.
is that a precise number for pi?
No.
What's wrong?
It starts with the 2 and pi starts with the 3.
Okay, actually, of course you're correct, but I want to impress on you the difference between precision and accuracy. This is a rather precise number for pi. It is 6 decimal places of precision. So it's a precise number. It just happens to be wrong. In fact, the very first significant figure is wrong. So obviously it's ridiculous. So you see the difference between precision and accuracy. Okay. The example that's given in your lab manual, which you will read, is think of a target. Okay, here's my target and my bullseye. And let's say right there in the center of the bullseye is sort of the God's eye truth. Now, let's say I shoot a gun and I get a bullet hole here and a bullet hole here and a bullet hole here and a bullet hole here. So Desiree, would you say that my gun is very precise?
Yes. No.
I agree with you. I think it's not very precise because look how far each of these is from my center, from the bullseye. But what about accuracy? Actually, this gun is not that bad accuracy-wise because the average of these actually is right there in the center. So I would claim that my gun is accurate, or at least accurately sighted in, even though it's not a very precision weapon. Now, what if instead, Christopher, what if instead I have a gun that does this? Here are my 4 shots. Right, like that. What would you say about that group in terms of accuracy and precision?
It would be precise,
Yes,
but not accurate.
but not accurate. However, I could sight it in better and it would be both, wouldn't it?
Yes.
Yeah. So, okay. So you know the difference between accuracy and precision. We know to use scientific notation. Now we have to talk about the concept of significant figures.
Professor?
Yes.
Yeah, quick question. Why is this topic so important, the precision and accuracy? Because I've taken chemistry, another physics class, and this topic always comes up, but like I still don't really see why it applies.
Oh, well. Well, there are so many facets to the answer to that question. In physics, we often measure things. In engineering, we measure things all the time. And we develop design data. Let's talk about engineering. Engineering is a better example. So in engineering, one of the things that we do all the time is to develop design data. We measure things to find out what the characteristics of the material is, as an example, and then we design and build something based upon those measurements. So I need to design a spar for a wing. My requirement is that the strength of that spar be a certain strength. I measure materials, figure out what the strength of the material is. Now I can use that material, provided that it is appropriate, in order to make my spar. I hope you can see how important it is that my numbers for the measurements I took for that material are accurate. Because if they're not, what am I doing? And in addition to being accurate, they need to have a sufficient precision for the purpose. So let's say that I measured a strength. Strength of material is given in terms of force per area. So newtons per square meter, or pascals. We'll learn all about that later. They're just words right now. But let's say I have a requirement that I need a material to have a strength of 100 gigapascal. So 100 times 10 to the 12 newtons per square meter. And I measure some material and I find that the value is 105, accurate to 3 significant figures. So I should write it as 1.05 times 10 to the 2 gigapascal. It would seem like it would work, right? However, I have uncertainty in my measurement, plus or minus 20 gigapascal. Is that going to be a good choice of material?
No.
So the answer is somewhere between 85 and 125, and my requirement is 100. But I haven't met my requirement. My expectation value is 105 gigapascal, but it could be as little as 85, in which case it's not going to work. So I've got to either choose another material or make a more precise measurement to get this number down so that I really know what I have. What if I have 105 gigapascal plus or minus 1 gigapascal? Now, I have high confidence that my material is going to work. So does that help answer why this kind of thing is so important, at least for engineering?
Yeah, that makes perfect sense.
Now, from the point of view of physics, let's say that we're doing an investigation of fundamental physics. Let's say that I'm Charles Auguste Coulomb in the late 18th century, and I am trying to measure the electrostatic force between 2-point charges. Coulomb's law actually says, you know what, let's use the universal law of gravitation. So Cavendish, Newton actually wrote this down, and Cavendish figured out what G is. Because we'll learn this later on. The force, the gravitational force between two masses is given by this formula. Well, how'd you come up with that? How do you determine that empirically? You have to make very careful measurements. First of all, careful measurements to decide what this value G is. It's a fundamental constant of the universe called the gravitational constant, but until you measure it, you don't know what it is. And you have to verify that it really goes like 1 over r squared. Maybe it goes like 1 over r cubed. Maybe it goes like 1 over r to the 1/2 power. Who knows? If you don't have sufficient accuracy and precision in measurements you're taking, you're never going to be able to decide whether or not this hypothesis that the gravitational force is given by that formula is correct. So another example, but more fundamental one. Okay, so let's talk about significant figures. So you're working a problem in mastering physics, and you're given data. And you're asked to use those data to do your calculation. So go back to the formula I had there before. You're given the masses, you're given R, what's the force? Okay. To what level of precision should you quote your answer? Well, the answer is you quote your answer to the number of significant figures that is the least precise input. So let's say you're given G, and G you can assume is exact. You're given M1 equals 1.01 kilogram. M2 is equal to 3.5 kilogram. And R is equal to 6.3715 meters. And assume the gravitational constant G is exact. It's actually measured to a very high degree of precision, and it's never going to be the source of error in your calculation. When you put all this together to decide what the value of the force is, how many significant figures should you use? What do you think, Truk?
Yes.
How many significant figures should your answer be if you combine these inputs?
It should be 7.
7
No.
significant figures. So you only know this to 2 significant figures. How are you going to know your answer to 7? Do you
I
see what
wish
I
it-
mean?
Yes.
So the answer is your least precise input has 2 significant figures. So you only really have 2 significant figures in your answer. Now you can quote 3 significant figures with the understanding that the 3rd significant figure is a little wishy-washy, and that's fine. So what I'll expect you to do is to quote your answer given the number of significant figures of your least precise input with possibly 1 more significant figure added just for the purpose of reducing round-off error for subsequent calculations. But no more than that. Every semester, especially in Physics 221, I get papers with answers to numerical problems that have 13 significant figures. Why in heaven's name would anyone quote an answer to 13 significant figures with inputs like these? The answer is because that's how many significant figures are on your calculator. But anything past the 2nd significant figure is really nonsense. So don't give me 13 significant figures just because your calculator gives you 13 significant figures. In fact, you can set the number of significant figures on your calculator. I always set mine at 4. So a mantissa and 3 decimal places. That's just to reduce round off error for subsequent calculations. But the final answer is usually going to be 2 or 3 significant figures. So go ahead and set your calculator to something reasonable and save yourself having to look at all those ridiculous numbers. Now, how do I determine the number of significant figures given a number? Well, this 1.01 obviously has 3. This has 2. This has 5. But what about a number like this? 1 point times 10 to the 5. Brandon, what do you think is the number of significant figures on that number as stated?
Centino,
Sorry?
are you referring to me?
Yes.
Okay.
I guess there's 2 Brandons, aren't there? So Brandon
Yeah.
Centino.
That'd be 6 significant figures?
No. No, remember, this is just the power of 10 for scientific notation purposes. The number of significant figures for this number is 1.
Okay.
The only significant figure is the mantissa. I don't have any decimal places.
Got it.
So this is a very imprecise number. What about 1.1 times 10 to the 5?
And this is still directed to me, right?
Yes, Brandon.
2.
2, exactly. Okay. Now, Joshua, what about this number? How many significant figures do you think are there, Joshua?
2.
Aha, I fooled you. No, the zeros are significant.
Oh, so it'd be 4.
It'd be 4. That's right, because putting a 0 here tells you I know it's 1.10, not 1.11 or 1.12 or anything else. The 0 is significant. And this 0 here in the 4th place tells you that it's 1.100, not 1.101 or something else. Sometimes numbers will be quoted with an uncertainty in the last decimal place, but we're not going to bother with that for data for problems. We will have to worry about uncertainties when we do our lab work. And we'll discuss that later. Okay, now, so here's the rule. Rules of thumb you can use. So news you can use. Generally, the data in your homework problems will be quoted to 3 significant figures. And the units don't matter. 1.1 times 10 to the 5 meters has the same exact precision as 1.1 times 10 to the 5 centimeters. So in scientific notation, those 2 numbers would have the same precision. Generally, you will have either 2 or 3 significant figures for inputs into your problems, unless otherwise you do not go wrong with 3 significant figures. 3 significant figures gets you within 1% in terms of precision. And that's good enough for most of our work. So if you were given these numbers here, you could quote 3 significant figures, even though this is really only 2. Just understand that that 3rd one is iffy. And if you quoted 2, you'd be fine. Okay, so 3 significant figures is almost always going to be the right answer. A number that is given without a decimal place at all is considered exact. So if this M2 were written instead as 35 times 10 to the minus 1, which looks awful, But what would it really mean? No decimal places, that number's exact. So you can consider that to have an infinite amount of precision. So if you're given a number like 5 centimeters or 5 meters or 35 kilograms or 35 times 10 to the minus 1 kilograms, those numbers are exact. So they do not enter into your determination of the significant figures of your answer. So the other inputs will control. What happens if all of your numbers are given to you as if they were exact? Use 3 significant figures as a rule of thumb. That's just going to be our convention. We don't really need more precision than 3 significant figures unless it's a special case. So if these numbers are all given as exact and you're not told what to do, 3 sig figs is fine. Okay, what about constants of nature? For example, G, you will learn, is usually quoted as 6.67 times 10 to the minus 11. And I won't put down the units. That's the value in MKS units. We'll figure out what the units are later. We'll talk about it. But in terms of just the number, consider that number exact. So any constants of nature, consider them to be exact. So what are the constants of nature you're going to use in this class? Probably only G. Now that I think about it, probably only that one. But constants of nature assume they are known exactly, and the number given you is an exact number, independent of how it's expressed. So don't use the constants for determining your sig figs. In reality, of course, you have to if you're doing a real calculation in physics, but we're going to consider them to be exact for simplicity. All right. I think that covers all of numerical literacy. So we need to go over the measurement and uncertainty exercises, but that, you know what, let's push that off until Wednesday and talk about vectors instead now, because I think we've had enough of this. So read the measurement and uncertainty handout. We will discuss how to calculate uncertainties in your lab work on Wednesday. And when we have our first lab, we'll go over it again with examples. Uncertainty analysis is something that students are extremely resistant to. I was resistant to it when I was a student. I don't know why, because it's so darn simple. But there's something about it that people don't like. When I was working in aerospace, we were doing, I worked on flight test for the B-2 bomber. And we were reducing data from in-flight measurements and radiosondes and stuff like that in order to demonstrate spec compliance in terms